So we're having uh and about topic two. Topic two we have hydrocarbons. Hydrocarbons that are compound containing carbon and hydrogen only. So the first hydrocarbon we're going to see the alkanes. In fact, before we even see alkanes or alkenes, how are these hydrocarbons obtained in large quantity or industrially? So therefore we call the process of fractional distillation. These hydrocarbons occur in the earth crust in the form of crude oil. In crude oil, there are various constituents or various components like kerosene, gasoline, and all the rest. In fact, is mixed together. So oil, lubricant, everything is mixed together. So you have to separate these various components using fractional distillation. How does fractional distillation works? Let's say you have a fractionating column of hydrogen. So here you have your crude oil, crude oil. You heat this crude oil, you heat. When you heat, what will occur? Evaporation. So evaporation will occur. Let's say it's 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees. So as you are heating, if it happens that 10 degrees or a component has having a boiling point 10 degrees occurs, at 10 degrees exactly, the liquid will turn into a gas and condense in the fractionating column. So the principle of fractional distillation depends on the boiling point of the various components inside the crude oil. So given that the crude oil component have different components, they will be separated into different fragments. So what's the difference between fractional distillation and simple distillation? For fractional distillation, the component of the constituent of mixture have the boiling point are so close together. Whereas for simple distillation, the boiling point are far, far, far away from each other. That's why we call it fractional distillation, because the distillation is done in fragmented way, in fragments. Okay, once we obtain these hydrocarbons, we have to break the hydrocarbons into hydrocarbons of smaller molecular masses. This is done using the process of cracking. So this is done using the process of cracking. Cracking. So cracking, this is the breaking down of hydrocarbon of higher molecular masses to form hydrocarbon of smaller molecular masses with the use of heat or a catalyst. If a catalyst is used, we call it catalytic cracking. If heat is used, we call it thermal cracking. So then now we can come down to our main topic, which is the hydrocarbons. We're going to start with the alkanes. So alkanes, I can take it as A. Alkanes are hydrocarbons having a general molecular formula Cn H2n plus 2, where n is greater than or equals to 1. So these alkanes are called saturated hydrocarbons. Why? Because they're characterized by a C to C single bond. So the table below gives the various alkane Cs. So here we have table N 1, 2, 3, 4, 5. Molecular formula. Structure. Structural formula. Molecular formula. Structural formula. Name. Okay, let's put 1 in the formula. We see what we're going to have. So putting 1 in the formula, we'll have C1, H. So I'm going to do for the first two, so that you can see. So C1, H2 into 1 plus 2. Let's read CH4. CH4. Yes, it's CH4. Methane. Okay. Let me put 2 in the formula and see what we're going to have. So we're going to have C2, H2 into 2 plus 2. C2, H, 2 times 2, 4 plus 2, 6. C2, H6. Putting 3 in the formula, let's see what we're going to have. C3, H8. Putting 4, we're going to have C4, H10. Putting 5, we're going to have C5, H12. So yeah, the structure CH3, 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 CH2, CH3, CH3, CH2, CH2, CH3, CH3, CH2, 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 CH3, 18, propane, butane, pentane. So these are the first 5 members of the alkane series. Their molecular formula, their structural formula, and their systematic name or the impact name. How can we prepare alkanes in the laboratory? This is the question that you need to ask yourself. Okay, well, alkanes. Then how can you prepare alkanes in the laboratory? So let's see how we can prepare alkanes. Advanced preparation. Laboratory preparation. 1. Hydrogenation. Hydrogenation simply means the addition of hydrogen. The hydrogenation of alkanes yield alkenes. So, hydrogenation of alkenes yield alkanes. So that's the reverse. Hydrogenation of alkenes. So, see the way we can do the reaction. So we can have an alkene CH2 double bond CH2 plus H2. Nickel catalyst 150 degrees Celsius to 200 degrees Celsius. The hydrogenation reaction is a syn reaction, meaning the hydrogen atoms from either side of the double bond. At the end of the day, we'll have CH2 double bond CH2 plus H2. So this is what we're gonna have: CH2 plus H. We're left with CH3, CH2 plus H again. We're left with CH3. We can have a decarboxylation. Decarboxylation. In this case, we are going to use a sort of carboxylic acid. We can use a sort of carboxylic acid like phenyl benzoate plus soda lime. Soda lime is a mixture of sodium hydroxide and calcium hydroxide. So have sodium hydroxide. That's reacting. At the end, we have benzene plus sodium carbonate plus maziba plus water. So we can also have a step-up reaction. Step-up reaction, otherwise called the Wool's reaction. So let's see the Wool's reaction. So in this case, in fact, before we see a Wool's reaction, let's talk a bit about the decarbonization reaction. In this case, you have a salt of carboxylic acids. So here you have phenyl benzoate or sodium benzoate plus sodium hydroxide. What will happen is that this COO plus this O, we are left with having CO3. So that sodium plus sodium, we have sodium 2 plus water. This reaction is possible with all the sort of carboxylic acid. So we can have a general reaction. General reaction can be like this: RCOO, sodium plus sodium hydroxide will give iron RH plus sodium carbonate plus water. So that's the general reaction. We can see the Wool's reaction. The Wool's reaction in chemistry is a very important reaction because it leads to an increase in the number of carbon skeletons. So the Wool's reaction. Okay, the Wool's reaction, the step-up reaction. So the step-up reaction, I'm going to give you guys the general formula or the general reaction. The general reaction is 2 Rx plus 2 sodium giving RI plus 2 sodium X. What does that mean? RA stands for an alkyl group. In fact, this reaction deals with a haloalkane. So that's a haloalkane with an arrow group. So I 2 Rx plus 2 sodium giving R at the plus sodium X. The arrow are equal, they're the same. So this is just a general reaction. So if I just did this reaction to you guys and I go, it'll be as if I'm quitting the desert. So let me give you an example. Having 2 CH3, and I can take chlorine plus 2 sodium giving CH3 CH3 plus 2 sodium chloride. So this can also go with a benzenic compound or an aromatic compound. So let me take an ethane compound or chloroethane. So you have chloroethane having 2E2 CH3 CH2 BR plus 2 sodium giving CH3 CH2 CH2. So map CH3 CH2. In fact, the compound double itself. So having CH3 CH2 CH2 CHE. You have 2 sodium bromate. So these are the direct way by which an alkane can prepare the laboratory. The Wool's reaction, hydrogenation, and also we can talk about the Clemmensen synthesis. The Clemmensen synthesis involves the conversion of carbonyls to alkane. This takes place in the presence of amalgamated zinc slash hydrochloric acids. So the Clemmensen reaction is usually advanced chemistry. So we're going to see the reactivity of an alkane. You know, alkanes are saturated hydrocarbons. They mostly react via free radical substitution reaction. So let's take free radical substitution or reactivity of alkene. Reactivity. Reactivity of alkanes.
reactivity. So against I go free radical substitution reaction. So let me write the equation on the board. We have methane plus CH4 plus Cl2 yielding CH3Cl plus HCl. The mechanism of this reaction occurs in three main steps: initiation, propagation, and termination. So the initiating step involves the formation of free radicals. So initiation. Initiation. The reaction is catalyzed by UV light. The UV light is a catalyst. So the formation of free radical, we have Cl2 depends on UV light. This Cl dot plus Cl dot. So propagation. Propagation. In the propagated state, the free radicals react with methane. So we have CH4 plus Cl dot then CH3 dot plus HCl. The CH3 dot react with CO2 to give CH3 CH2 Cl plus Cl dot. So one terminating. Termination. Termination here means recombination. All the radicals have been formed, recombine to form neutral molecules. What does that mean? Cl dot plus Cl dot combine to give Cl2. CH3 dot plus CH3 dot combine to give CH3. CH3. Alkane mostly undergo free radical substitution reaction. So the mechanism of the reaction is on the board. Either I initiating step, the Cl2 dissociate to give under the influence of UV light to give Cl dot plus Cl dot. In the propagated state, we have CH4 plus Cl dot giving CH dot plus HCl. We have CH2 dot plus Cl2 giving CH3Cl plus Cl dot. In the terminated state, we have the recombination of the radical. Cl dot plus Cl dot give Cl2. CH3 dot plus CH3 dot giving CH3 plus CH3. So the mechanism occurs in three main steps: initiation, propagation, and termination. So we're going to go through the alkenes. Then all of the alkenes is different from alkanes. Alkenes and alkynes are unsaturated hydrocarbons, and they will show different reactivity. So in most cases, I'll also do the reaction the time